Each one of these uranium fuel pellets releases enough thermal energy That breakthrough inspired Marie and Pierre Curie to discover other radioactive elements, including radium and polonium. In 1932, James Chadwick discovered the neutron, the subatomic particle that would become the key to nuclear fission. Just a few years later, in 1938, German chemists Otto Hahn and Fritz Strassmann demonstrated that uranium-235, a rare isotope found in natural uranium, could be split apart when struck by neutrons, releasing enormous amounts of energy. Natural uranium consists of 99.3% uranium-238, which doesn't readily undergo fission, and just 0.7% uranium-235, the reactive isotope capable of sustaining a chain reaction. The process of artificially increasing that proportion is what we call enrichment. During World War II, the United States brought together the greatest scientific minds of the era under the Manhattan Project, led by figures like Enrico Fermi and Robert Oppenheimer. They developed and refined enrichment techniques using gaseous diffusion and high-speed centrifuges capable of separating isotopes based on their slight differences in mass. The most dramatic outcome of that effort was the little boy atomic bomb, dropped on Hiroshima in August 1945. Which used highly enriched uranium-235. After the war, attention shifted to the peaceful application of nuclear technology. For use in power plants, uranium only needs to be enriched to between 3% and 5% uranium-235. Weapons-grade uranium, by contrast, requires enrichment levels above 90%, which is why nuclear proliferation remains one of the world's most pressing concerns. Today, enriched uranium fuels reactors that generate roughly 10% of the world's electricity. Everything starts underground. Countries like Australia, Kazakhstan, and Canada together account for more than 60% of global uranium production. The element is primarily found in a mineral called uraninite, typically at concentrations between 0.1% and 2%. But in the Canadian province of Saskatchewan sits the highest-grade uranium mine on Earth, where ore concentrations and radioactive exposure. The mine is continuously ventilated, with fresh air circulated every 20 minutes. Once brought to the surface, the ore passes through a radioactivity scanner that confirms uranium content, typically between 15% and 18%, which is considered exceptionally high quality. The ore is then crushed, ground into a fine sand, mixed with water to form a slurry, and pumped to the surface. Specialized trucks haul the mixture to a processing mill about 50 miles away. At the mill, the slurry is treated with acid, which selectively dissolves the uranium while leaving other minerals to settle at the bottom of the tanks. The uranium-bearing solution is drawn off, purified through a series of chemical reactions, and heated to 1,560 degrees Fahrenheit. The uranium is then converted into uranium hexafluoride gas and fed into high-speed centrifuges. Inside those machines, the slight mass difference between isotopes causes uranium-235, being fractionally lighter, to concentrate toward the center of the rotor, where it can be separated. The result is a dense, dark powder that's packed into sealed 55-gallon steel drums, clearly labeled with radioactive hazard warnings. Those drums are shipped to a nuclear fuel manufacturing facility. There, the uranium undergoes further chemical transformations, moving between different oxide forms until it becomes uranium dioxide powder with precisely the right properties for pressing. Using several tons of hydraulic pressure, that powder is compacted into small cylindrical pellets, roughly the size of a peanut. A single pellet holds the energy equivalent of 1,800 pounds of coal, or roughly 150 gallons of oil. The pellets are loaded into industrial furnaces and sintered for 24 hours at extreme temperatures. This process eliminates internal pores, increasing the material's density and structural stability. After the furnace, robotic arms stack 30 pellets inside zirconium tubes, a metal that's exceptionally resistant to heat and corrosion, and critically, one that allows neutrons to pass through freely during the fission reaction. The tube ends are sealed by automated welding to form finished fuel rods. 37 fuel rods are then bundled together into a structured fuel assembly, which is weighed with precision to verify the exact uranium content. Before being loaded into a reactor, the radioactivity emitted by these assemblies is low enough that workers in proper protective gear can handle them safely. Once delivered to the nuclear power plant, the fuel assemblies are loaded into the reactor core, which holds up to 5,760 rods distributed across 480 fuel channels. Fission begins when neutrons collide with uranium-235 atoms, splitting them and releasing both energy and additional neutrons that go on to strike other atoms. This self-sustaining chain reaction generates immense heat, carefully regulated by automated safety systems. The reactor itself is encased in 6-foot-thick reinforced concrete walls and is designed to shut down automatically if temperature or pressure reach critical thresholds. The heat produced converts water into steam, which drives massive turbines housed in buildings 1,300 feet long and the equivalent of 20 stories tall. Spinning at 100 revolutions per minute, each turbine drives a generator capable of producing more than 750 megawatts of electricity, enough to meet the energy needs of 500,000 people. After roughly a year in operation, the fuel assemblies are spent. At that point, however, they're so intensely hot and radioactive that they must be submerged in cooling pools, 26 feet deep, for at least 10 years before they can be safely managed as waste. More than 700,000 spent fuel rods currently rest at the bottom of these pools at facilities around the world. Thank you for watching. If you have suggestions for our next video, share them in the comments below. Don't forget to like, subscribe, and stay tuned for more stories through Stories Behind Everything.